morning. So you can think about if you had any questions for the morning. All right, so I was wondering if anybody had any questions from the morning or from yesterday. Awesome, everything is crystal clear. So I know at the end of last time what we were discussing is how our agent can start to learn to act and learn the optimal Q function. And then we started to talk about not just learning the optimal Q function, but in fact making your optimal decisions. And I talked to you extremely briefly about function approximation, which I think is a really important, it's one of the open frontiers. Both empirically it's working very well, but there's a lot of theoretical questions about when and why it'll work well. So what I wanted to do in this lecture is to talk about sample efficient learning. And before I do that, I just want to highlight a little bit about why I care so much about sample efficient learning. And part of it goes from sort of the historical legacy of thinking about sequential decision making. So I was arguing before that we've sort of seen this amazing legacy of sequential decision making under uncertainty since Aristotle, people thinking about this, and then in the 1940s really starting to think formally about multi-arm bandits, and then reinforcement learning starting in the kind of 1970s, 1980s in the way that we define it now. And in a lot of the ways that we're seeing amazing improvements right now, it's been in these sort of domains. So it's been in domains like robotics or video games where we have a simulator of the domain, and then we can do many, many, many trials until we can figure out an optimal policy. And so that might mean that we might need some enormous amount of data to train, but that's okay because as long as we can train our Go agent such that it reaches, superhuman performance, that's sufficient for when we actually deploy it. And we can always try out any strategy in the domain because if we fail, it just means that we're failing to play Atari well. It's not really hurting people in any way. But I think that in parallel with this interest in making artificial intelligence and reinforcement learning agents that can exceed human level performance has been sort of a version of thinking about what are the types of agents we want to create that are going to assist people, like teaching machines, which I've shown here. And if we think about agents that are going to be trying to help us with tasks, it introduces a different set of constraints and a lot of really interesting technical problems. So if we think about having a reinforcement learning agent helping to enable a student to learn a new domain or be in the use or context of clinical trials, one big challenge is that we don't have a good simulator. We don't have a good simulator of how people learn. We don't have a good simulator of people's physiology or their consumer behavior. And so that means we can't just use a simulator to necessarily train our algorithms. But at the same time, that if we gather things from real experiments, like we really try things out on real people, then that affects those people. And so that raises a lot of challenges in terms of the way we're going to have to build reinforcement learning algorithms if we want to tackle those forms of domains. So a lot of the work that I think about is sort of techniques to minimize and understand how much data is actually needed in order to learn to make good decisions. And the implication of this is not only would that help answer some of the foundational questions of reinforcement learning, but that if we could solve this well, that means we're just going to be able to help more people, because if we need less data to figure out what's the right thing to do, then more people can benefit from that optimal policy. So that's why I think it's such an exciting frontier to consider. And when we start to do that, then we need frameworks to decide, well, what does it mean for us to be efficient? Or what does it mean, how do we quantify how much data is needed? And can we bound that and can we compare it between different forms of algorithms? And so one framework that I'm assuming they talked about last week was PAC. Did people talk about PAC last week? Or you've seen it before? Great. So probably approximately correct reinforcement learning thinks about this in the context of sequential decision making. And the way we're going to define this is by saying we want to have a bound such that with high probability, so probability at least 1 minus delta, delta is an input parameter, we want to say that the decisions that we make, which is going to be indexed by v pi t will be the policy that we're following on a particular time step. So we would like to be able to say that the number of time steps where the value of the policy we're following is close to the value of the optimal policy minus epsilon. In this case, epsilon is an input parameter. So we want to say we're near optimal for a number of time steps which is finite. And it is going to be defined in terms of the size of the state space, the action space, epsilon, and delta. Okay. So we're going to define this part, the number of essentially mistakes we're making, as the sample complexity. And we want to say the sample complexity is bounded where we want f to generally be a polynomial function. It's not always. It can be exponential. And so this is going to be the definition that we use of PAC. This was introduced maybe around like 1998 to 2002, where some of the pivotal papers came out of quantifying how much data was needed for tabular settings. So now we're going to go back to the tabular sort of discrete state and action space for most of today, but there's a huge amount of excitement in extending these results to the function approximation case. So this is the definition of PAC, and we're going to say that's one notion of algorithms being good, and the way we can compare it is in terms of normally these quantities. What is the amount of mistakes our algorithm is going to make, regardless of the domain on which it's deployed. So that's the definition of PAC in the context of reinforcement learning. Regret bounds, also I'm sure Kevin talked a lot about regret. Regret bounds in the context of reinforcement learning are going to look quite similar. Actually, I'm just going to highlight one thing because PAC and regret are quite different in certain ways, and I want to highlight why. So what PAC is saying here is for the states that you encounter. So we're in the sequential decision-making case. We're going to be making series of decisions. The decisions that we make are going to affect the next state we reach. So again, if instead of coming to this class, you had decided to go get coffee, you might have had a wonderful existence, and you'll never know. And in that case, you would have reached a different series of states. What PAC is evaluating the algorithm on is the mistakes, the number of mistakes you make based on the states that you reach. Okay? So you could have, let's say you're in a really adversarial world where either you make the right decision on the first time step or you don't. And then after that, your world is wonderful or your world is horrible. So from the PAC learning perspective, if you make a wrong first decision, that would be a mistake of 1. But then after that, if you're in the really horrible world, you won't continue to get sort of dinged here for making more mistakes because you're always being evaluated with respect to the best decision you can make at the current time step. So in some ways, that is a less stringent version than regret. Regret says something stronger in many ways. Regret says what I'm going to do is I'm going to compare what if you were to act optimally from the very beginning onwards versus how you actually acted, and compare the sum of rewards you get. So that's stronger because their regret would say, well, you should have made the good first decision, and if you did, you would have gotten infinite reward from then onwards. Because this is being evaluated on 2 different state distributions, essentially. This is saying what would be the sequence of rewards you'd get if you start off acting optimally, and then you went through the trajectories as if you were always acting optimally, versus the trajectories along the decisions you actually make. I just wanted to highlight that they're going to reach different distributions of states and actions. So what regret is saying is that it's not trying to count mistakes. It's just comparing the sum of rewards we get under the optimal policy and expectation versus the sum of rewards we get under our actual decisions we make. And again, we want to bound that. And I put up here a high probability regret bound, but often people do expected regret bounds too. So these are slightly different frameworks. Both of them are very popular. In the bandit setting, regret is much more common. In the reinforcement learning setting, I think now you're starting to see a little bit more regret. In general, these have both been considered extensively. Okay, so our goal is going to be in this case to try to be able to compare algorithms in terms of their regret properties and in terms of their PAC properties. And these 2 frameworks are not necessarily always interchangeable. In terms of algorithms that have good regret properties, often have good PAC properties, but if you're good in one, you may or may not be good in the other. Yeah.
Here F is going to be an operator down, so however we're going to move forward. But in the previous example, when you had it in terms of the sample, so shouldn't that be like bigger than, like in this one? So
yeah.
basically the first term is the number of time steps where we are good because we're almost close to the optimal.
Yes.
And then
the number of time steps where you're bad. Right, this is saying the number of time steps where you're bad, where the value you take, I'm assuming rewards are positive, so this is saying where the decision you make, the value of that decision, is worse than near optimal. So this is the number of mistakes, the number of times you're not epsilon close. Any other questions about these two frameworks? Yeah.
When you write S and A there,
Yes.
is that magnitude of S?
Yes.
Or-
Thanks. Yeah, this is going to be in terms of the cardinality of the state in the action space. Yeah.
So you're comparing the expectation to like the actual trajectory. Is that true? So then you could technically follow like the optimal policy, but still have the regret.
Yes, great. So normally we're going to have this. It's a good question. I mean, a little loose on notation here. In general, we're going to be wanting to compare. They're slightly different frameworks, so I'm going to be slightly informal about that today. But yes, so you could have cases if you're evaluating along a single trajectory where you do better than optimal regret for a particular trajectory. In general, we're going to want to think about expectations of the expected regret, because if these are stochastic transition models, then generally this is going to vary substantially, and so we're going to think about, on average, in expectation, what would be the expected regret under the optimal policy versus this. For a particular run, you could have a negative regret. Good questions. Any others? Okay, so what I'm going to try to do now is talk a little bit briefly about kind of where we are for a particular, slightly simpler Markov decision process type, and then use that to motivate some of the techniques that have been done to try to achieve those results. I'm going to go to here. So to do this, I'm going to talk about tabular episodic reinforcement learning, all in the discrete state and action space. This is a simple, this is a subset of all the MDPs we'd want to consider, but I think it's an interesting subcase, and it's very useful for things like, I mean, not the discrete aspect, but the episodic case, I think, is quite reasonable in many practical applications. So in this situation, what we're going to think about is that we're going to have a single episode which has 8 steps, where at each time step, we're going to be in a state, take an action, and get a reward in next state. We're going to repeat this H times. So we can think of just being a case where we have episodes of length H, and then we repeat these over time. Okay. And you could imagine that H doesn't have to be identical at each time point, that maybe we have a terminal process before that. But for simplicity today, let's just assume that everything is of length H for each of the episodes. Okay, so in this case, what do we know in terms of how hard it is? Hardness here being quantified in terms of regret bounds. Lower is better, pack bounds, lower is better for this particular setting. Well, I mentioned to you before a very simple approach to trying to figure out how to act in the world, and that was to be greedy, or epsilon greedy, with respect to your current estimate of the Q function. So just to recall from that, when we talked about greedy in the limit of infinite exploration, we talked about greedy in the limit of infinite exploration, and we talked in particular about epsilon greedy algorithms, where with probability epsilon, we act randomly, random A. And with probability 1 minus epsilon, we do argmax of our current estimate of the Q function. And we talked about how that was sufficient in the tabular case to converge. And what was shown is that, unfortunately, even though that's sufficient asymptotically, so you will converge to the optimal Q function in that case, and you will be guaranteed to be following that the optimal policy, the amount of data we need from the pack side can be exponential, and from a regret side, we can have order t. So t here is going to be the number of time steps we're acting, and essentially it means we could have linear regret. You could continue to make mistakes forever. So that's not ideal. That indicates that either whether we're thinking about from the pack setting, we could need a really large amount of data in order to learn what the right thing is to do, or from a regret setting, we could suffer linear regret. And there's lots of other really trivial ways to achieve linear regret, like always take the same action. So why does this happen? Just as some of the intuition, the first part might be sort of already some intuition. If you have to do strategic exploration to reach somewhere, so let's think about something like a long chain that I mentioned before, which you can think of as being sort of related to playing games or cases where you only get a very delayed outcome. So you could have transitions that maybe go back and forth between this long chain with different probabilities, and you have to take exactly the right sequence of actions. perhaps another more simple example for that would be like a combination lock. When you unlock your bike, you have to do exactly those series of numbers, and if you don't do any of them correct, you don't get a reward. And so if you're trying to search through that space, that could be exponential. So that's sort of the intuition for what these results were. And then starting with Satinder Singh and Michael Kearns, and some other really lovely work, and Ron Braffman, in the 1998, 2002, people started to have bounds that were polynomial for the pack setting. So they started to be able to have results that we got polynomial sample complexity. So we don't have to be exponential in the size of the state space. So, but instead we can have much stronger bounds. And then really over the last like 10 to 15 years, a lot of work has been done until now we basically closed these two cases. So this is my student, Chris Dan, who's done a lot of work during his PhD. There's been some really nice work by Michael Lippman and his colleagues, as well as from really nice work from DeepMind thinking about this, and some others. And so what we now have is from the DeepMind, Ian Osband and Mohammed Azir and Remy Munoz, they provided tight regret bounds for this case, which scale with the size of the horizon, the size of the state and action space, and the time step. And on the pack setting, as of this year at ICML, we have a tight bound now for the pack setting. Now these are worst case bounds. These are saying that no matter what is the MDP that you run on, these are the bounds you're going to achieve. Now this is, as you can see, we're at least linear in the size of the state space for the pack setting, or and square root of S. And so if you want to scale up to really large state and action spaces, it's clear we'd want to do something different than these types of approaches because they're not going to scale very well. I just want to highlight that these are all worst case bounds. And what we see empirically is often it is much, much better. So I always encourage my students to instantiate their bounds because I think it's illustrative. And the first time I remember instantiating these bounds was when I was in graduate school. And at the time we were more in kind of this level of the spectrum, but nevertheless, I was instantiating it for a very small Markov decision process, and I realized it said we'd need something on the order of like 10 to the 9 samples per state action pair, which was a little bit dispiriting. And not, maybe now we're down more to like 10 to the 3 or 10 to the 4, but still empirically we often need 10. So our theory is telling us we need, somewhere between 10 to the 3 to 10 to the 9, and empirically we need 10. And maybe some of that is due to generalization, but some of it is just because many problems are actually much, much easier than what this theory would predict in the worst case. So typically for these lower bounds, we construct very hard, simple cases of MDPs and show that we need a lot of samples to learn there. But there are known cases where it's easier. So for example, bandits are easier than Markov decision processes. They have tighter bounds. Deterministic processes are also easier, as you might expect, because you only need one sample for each state action pair to learn the dynamics model. So there are known subcases which are easier. But one of the things that we looked at recently and we were curious about is, well, you don't want to have experts to know whether you're in one of these particular subcases because it's not always obvious. So could we have an algorithm that provides problem-dependent bounds? And so that's what Andrea, your TA, and I showed recently, which is, and this was known empirically before, but now we can prove that it's actually provably more efficient, that in the case in fact, you don't have to depend on the horizon directly, you need to depend on a problem-specific constant, so you can get better problem-specific bounds. Okay, so this is sort of the recent things that have been happening over the last 10 years in the tabular setting. There's a lot of really exciting work that's happening in the function approximation setting. I think there's also more work to be done over here. Kevin and Max, who's a graduate student at Berkeley, have some really nice results on this recently as well. So the problem is not closed yet, but I wanted to illustrate sort of what were the main ideas. How do we move, in particular, how do we move from here to here? I think is perhaps one of the first really big jumps. And then ideally, if I have time, I'll give you some insight about how we've moved from here over since then. And the nice thing is that these are pretty simple ideas. And the key thing is actually to be optimistic. And I think that's quite lovely that we can show mathematically the right thing to do is to be optimistic. So let's look at that. And to show that, I'm going to introduce an algorithm which is called model-based interval estimation. So let me get that up. And if we could move this up, that would be awesome. Okay, so model-based interval estimation with an exploration bonus. It's going to be an algorithm for acting online. So again, we don't know the dynamics or reward models. And what the key idea is, I guess I'll say two key ideas. So if we think about the algorithms that I've been presenting so far, a lot of them have been model-free in the sense that we're trying to estimate a value function directly, but we haven't talked very much about learning dynamics and reward models. What you could imagine instead doing is to try to explicitly estimate a dynamics and reward model and use it to compute, using value iteration or something else to compute a value function. So that's what we're going to do now, and we're going to do it in a special way. So here's the MBIE algorithm. And this is due to, this version is going to be from Strell and Littman, 2008. But I'll highlight that the ideas behind this maybe came out first around 1994. Leslie Cabling, I believe, in her PhD thesis, introduced some of these ideas. There might be even earlier notions of them in MDPs, but that's certainly one of the first ones I know of. Okay, so what this algorithm is going to do is it's going to take input of epsilon, delta, and m. And then what we're going to do is we're going to keep track of a few different things. We're going to keep track of counts. So I'm going to define n of s, a, s prime equaling to 0 for all s, a, s prime. It's just how many times have we seen the tuple s, a, s prime. And I'm going to keep track of an empirical reward. I'm going to call it r hat of SA, which is going to be equal to 0. And I'm going to keep track of an empirical Q, SA, which I'm going to initialize differently. I'm going to initialize this as 1 divided by 1 minus gamma. And I'm going to assume all of my rewards are all bounded between 0 and 1. This is also for all SA. Okay. Then we're going to initialize our initial ST to be equal to S0. And then the loop goes as follows. So forever, what we're going to do is we're going to take an action which is equal to argmax of our current Q. Okay, so we're just going to act greedily with respect to our current Q function. We can break ties randomly. You certainly should break ties randomly. It's a common error in code not to, and that can have implications. But you just randomly break ties here. And then we're going to observe, we observe a reward and a next state, so RT and ST plus 1. This just comes from the environment. We're acting in the world. And then we're going to update our estimates of the dynamics model and the reward model. So we're going to maintain an R hat for SA, which is going to be equal to 1 over sum over all S prime n of SA S prime. This is just saying how many times have we experienced that state action pair times RT plus sum over T n of SA S prime divided by, this is plus 1, times R. You can tell me if I've made a one-off error, but essentially it's just averaging the rewards that we've ever gotten in the state action pair. So we just have an empirical average. We have a maximum likelihood estimator of this part. And then we're also going to maintain a transition model. So I'm going to say that my P hat of dot, I'm using the dot here to indicate that we're updating the whole estimate of the transition model for the state action pair, is just going to be equal to the number of times we've seen SA S prime divided by all the S primes. So again, this is just the empirical transition model. We just take all the counts, and we average. So this is also often called a certainty equivalence. approximation. Certainty equivalence means that we're ignoring any uncertainty in our estimates in this case. So we take our data, we compute an empirical, so this is our empirical reward, and our empirical dynamics model. Now it's going to be wrong. It's particularly going to be wrong at the beginning because we've only observed one thing, so this is going to be likely hopelessly wrong. Right? We'll also have to have figured out some way to initialize this for all the other state action pairs. Doesn't matter how you do it. You can do it uniformly. You can just pretend that there's a probability of transitioning to any of the other state action pairs. So we do need to initialize that too. So I'll write that here. So you could say start with a uniform, for example. Okay. And then the important part is how we compute the new Q. So we have these transition models, and what we're going to do is, while not converged, this is just going to be us essentially doing lots of value iteration with these empirical estimates plus a bonus term. We're going to have Q tilde of SA is equal to R hat of SA plus gamma. This is where we're using our empirical estimates. Max over A prime Q tilde of S prime A prime plus, switch pens because it's getting a little bit bad. Yeah.
About the motivation of this, so we're trying to do Q learning, but show that it's more efficient than.
Great question. So it's not going to be Q-learning anymore. It's going to be a different algorithm. But we are trying to do control. We're trying to learn online, and we're trying to do it in a way so that we could get Q-learning with epsilon greedy can be exponential in terms of the amount of data we need. And this is going to be an algorithm which is polynomial in its amount.
So some complexity of the algorithm is going to be better than the Q learning.
Yes. With Q-learning with epsilon greedy. Yeah. So there's been recent nice results from Chi-Jin from Berkeley showing that Q-learning can also be PAC, probably approximately correct. If you do two important things, you have to also include some notion of optimism in Q-learning, and you have to change the learning rates as well. It's a nice paper. Yeah.
So we can see that you approximate the model and then do value iteration iteratively. What about we just approximate the model at once with a lot of samples together, and then we do the value iteration?
Yes. You mean like, could you do all of this? Could you gather a bunch of data and then do it?
Yeah. It's better.
Well, we're using this after each time point to change how we're acting. Does that make sense? So we can't, you'd have to be figuring out some way. You wouldn't want to do this like 100 times, a large number of times before updating Q, because you won't get to benefit from your updated information. Does that make sense? Yeah. So what this is saying is that, so this is this is an inner loop to that bigger loop. So it's saying I get a state, action, reward, next state tuple, and then I totally change my Q function. Not just for my current state, but for all other states, any state in the state space. Because I'm doing value iteration. Let me just quickly write down the last thing in here because this is important. So plus eta, and then I'm happy to answer questions. N of, let me just, sum over S prime, N S A S prime, okay, for all S A. Let me just say what this equation is doing. This looks almost like a Bellman backup, but a couple changes. We're using the empirical reward, we're using the empirical dynamics model, and we're adding a bonus term, which is beta, divided by the number of times we've sampled that state action pair, square rooted. And we do this many, many times. So we can think of this as doing value iteration here. We do that until this is converged or converged to some accuracy, and only then do we take the next action. which means that we can immediately benefit from that information. That's also different than Q-learning, where in the basic version, we just throw away the data after that. We don't do this kind of additional propagating of information to all the other states. Yeah?
So like estimating the reward and the dynamics, and then doing what we did in the first lecture, when we do value iteration, as if we knew.
Exactly. It's exactly like doing value iteration as if you knew, except for you're plugging in your empirical estimates instead of the true ones, and critically, you're adding a bonus term. And your bonus term depends on how many times you've seen a state action pair. So if you've seen this a lot, your bonus term is going to shrink a lot. And if you haven't seen it much, it's going to be enormous. And what is that doing intuitively? Intuitively, it's saying, I'm going to behave as if state action pairs are good, either if I've seen empirically they have high reward, or they lead to high reward, or I just haven't tried them very much. Yeah?
So that's still in the sum, because it has an S prime.
Sorry, I just put this, I didn't use a separate, we could also just have had NSA. That's what this is. So this is separate.
Shouldn't the max be also contain the reward?
No, this is the like max next state. Any questions? Yeah.
Do you know if just the R hat and the B hat?
Sorry, what?
If you took the R hat and the B hat and had an algorithm now run on just those, if this was your model,
Yeah.
how good would that be? I don't know, like.
Yeah, we don't have a bonus term. Yes. So the question is, if I don't add this bonus term, how good is the algorithm of this? It really depends. In some cases, that's great. What that means is that you don't need to do any strategic exploration. It means that you're gathering any information you have. In some ways, you're being reflective but not prospective. So you're always using your new data to try to make better decisions, but you're not actively trying to see things out. In some cases, that can be very bad. In the chain example I showed before, or the combination lock, imagine that it's like a combination lock, but like, I don't know, it like sort of opens a little bit if you get the first one right, but it doesn't actually open fully until you get it all the way there. So you get like a really large reward for one thing, but a tiny reward before. In that case, these sort of ones will do very badly if you don't have your bonus term, because you get a little bit of reward and think, oh, I'll use that, and you won't think about the fact that you might need to act really strategically in order to get the long-term reward. Most problems, fortunately, aren't that pathological, so in practice, certainty equivalence often works really well. Yeah?
So intuitively, this is kind of similar to UCB.
Absolutely.
But there's no logarithm term. Why is that?
Yes. So we are going to, this is, what's going to happen here is we're going to do a finite number of updates. And I didn't write that here, but I will add that. So we will no longer update our models after M samples. So a lot of the early results used, skipping ahead a little bit, a lot of the early results used union bounds to try to, over all the times you'd update your models in order to get results, and so that they didn't have to take union bounds over an infinite number, they stopped updating at some point. So like, let's say you get M samples of state and actions, then you don't ever update after that, and that makes it easy to update, to write down your union bounds over all the updates. That is dissatisfying on two levels. It's dissatisfying because you always want to be able to use more data to improve your estimates. And it's also not very elegant on the theory side. And so things like law of iterated logarithm and other approaches that have been used in bandits have now, we and others use it in the RL case. So that was not used in this particular algorithm, but you can certainly incorporate it. Yeah?
So we are adding this exploration term just to trade off between the fact that we do not really know the reward and dynamics, so it's going to help us to explore just due to not knowing exactly.
It's both, yeah. So it's both that we don't know them, but also that we're assuming at least the dynamics model is stochastic, and so that you'll need more than one sample to get a good estimate of it. So if you're in a deterministic world, then you may need some optimism to kind of get really far out, but you only need one sample to learn your dynamics model. But if your world is stochastic, or like in bandits, if your reward is stochastic, if you try things once, you might accidentally get a low reward, even though on average you do better. So the optimism is helping us, just like in upper confidence bound approaches for bandits, it's helping us to continue to try things until we're confident over those estimates. Oh, great questions. Any other questions about how the MBIE proceeds? So MBIE proceeds in this particular way, and I can write down what beta is. So beta incorporates a log term. I guess it depends where you meant where you thought we were missing a log. There's a log term in the beta. So there's Okay, one second. I get that. Okay, so this is a pack algorithm. It has a finite sample complexity bound. And I want to write out briefly what are the conditions we need. What is a set of sufficient conditions for an RL algorithm to be pack? And then we can talk about the fact that MBIEB is one of those such algorithms. So here's a set of conditions. Yeah. M in this case is the number of updates we do for a particular state action pair in order. It's a maximum upper bound of how much data we use to estimate the reward in the dynamics model.
Is like the loop supposed to go from 1 to n?
No, the loop goes forever. Loop is like every time I'm taking an action. This is saying that how we compute our hat, and what M does is it says we throw out samples after M. So if the number of counts of NSA, this is just the number of times we've tried state action in that, if it's greater than M, then we only use the first M samples in there.
Where do you see this?
I didn't, I wrote it over here. Yeah, I said it. We no longer update the models after M samples. All right, so what is the sufficient, here's a sufficient set. It's not that, this is not required, but sufficient set of conditions for a PAC-RL algorithm. First is optimism. Which says that our computation of QT, of SA, I'll put a tilde there, has to be a number that is greater than Q star of SA minus epsilon for all SAT. Which says that the value we are computing needs to be optimistic, or with respect to the true value, minus epsilon for all time steps. Just intuitively, does anybody have a sense, maybe from the bandit part, of why it's essential to be optimistic instead of pessimistic? What the problem can be with being pessimistic? We're adding a bonus term here. We're not subtracting one. So we have an idea of why optimism might be helpful for acting. Yeah?
I think yes. So, optimism, if optimism means that you're expecting to get better rewards in exploring options that you haven't previously explored, then you're doing better exploration when you're more optimistic, right?
Yeah, and it's also that, if you happen to be unlucky and get a low reward for that, that's right, that's sort of the direction, and it's saying if you happen to be unlucky and get a low reward for a state, you'll continue to try it. Under optimism and pessimism, you might not, which means that you might be make mistakes forever. If the world is giving you a low sample early on. So it says optimism. Second is accuracy. What accuracy says is that our V tilde that VT of S minus V M pi T. We'll talk more about that later. Is less than epsilon, and the MDP, we have a true MDP, and then we have an MDP, which I'm going to denote like this. And what this is going to say is that are values between the true value of a state and the value of a state in this particular MDP I have not told you about, under the current policy are close. And the third is bounded learning complexity. Bounded learning complexity. Okay. Which means the total number of updates to Q and the number of times we visit an unknown state action pair. Say pair. Is bounded by theta of epsilon delta. I haven't told you what an unknown state action pair is, but an unknown state action pair is going to be one for which we don't have a good dynamics model and reward model, and where we haven't experienced it m times yet. Now, this is a little bit less. This has gone away in terms of future algorithms. We can now update things forever. This formulation of thinking explicitly, of essentially having a threshold between the parts of the state action space that we know really well and the parts that we don't, having like a hard classification between those two, has also gone away a lot over the last 5 years. It makes for nice, clean analyses. It's, again, not always something that you want to do because you want to be able to continue to update forever. And it basically, it's not as tight as what we would like to, but it makes some of the analysis simpler because then we're just sort of classifying our level of uncertainty over a state action pair. And we're saying that once something becomes known, we're going to have an accurate estimate, a sufficiently accurate estimate of its dynamics and reward models for some of the things that we require. So in these cases, if all three things of these hold, then an RL algorithm that is executed on any MDP will follow an order epsilon optimal policy. So we're not going to be tight with respect to constants. And typically we're not tight with respect to log terms either. Often we drop both of those and use O tilde notation. On all steps, all but order our learning complexity divided by epsilon times 1 minus gamma squared log 1 over delta log 1 over epsilon times 1 minus delta with probability steps. Probably least 1 minus 2 delta. So we can see that this is saying that if we have an algorithm that satisfies these three conditions, and MBIEB does, and we'll talk about that more in a second, then then running that algorithm will be a pack algorithm with a pack complexity that depends on your learning complexity divided by epsilon times 1 minus gamma squared times some log terms with high probability. And one of the interesting things that goes to one of the questions before is it doesn't tell you where these mistakes are happening. It just says that the total number of mistakes will be bounded. It doesn't say that these mistakes will happen at the beginning necessarily. It just says that if you run this algorithm forever, it won't make more than this many mistakes with high probability. Yeah?
In the algorithm, the loop here, you didn't say, are you going to only stop after you visit every signal state action pair anytime? Or?
Oh, sorry. We're going to loop forever. So t is going to be equal to 1 to infinity. So So we're going to be doing an RL algorithm that is acting forever. We're going to continue to go. It's easy to change these between infinite horizon problems and episodic cases. In that case, instead of having t equals 1 to infinity, you'd have an outer loop, which says for each episode, I act for each time steps, and then repeat. This part is just about how often we're updating our empirical models. I know this might be a little confusing because it's on the side. So if anybody has any other questions about how the algorithm works, let me just step through it again. We initialize our rewards to be 0 everywhere. We initialize our Q function optimistically. So this is optimistic because our rewards are bounded between 0 and 1. We have a discount factor, so all value functions are going to be upper bounded by 1 over 1 minus gamma. So this is an optimistic initialization. And then what happens is we start in a state. Now we're going to do infinite horizon acting forever. What we do is we take an action that is greedy with respect to our Q tilde. We observe our reward in next state. And then we update our empirical estimates of the state action the state we're in and the action we took. And the same for the transition model. If we have more than m data points for that particular state action pair, we only use the first m. And then given the empirical transition and reward models for all of our state action pairs, we do value iteration, where we add on a bonus term that is dependent on the number of times we visited that state action pair.
Practically, when you implement it, what is your rule to stop the loop? Because like for the bell and backup, yeah.
Nothing. However long you want to run. Yeah.
Like with the bell and backup, you had like if it's within epsilon or whatever.
Good question. Okay, so in value iteration, we were just doing planning, and so that means that we know the dynamics in our reward model. We were just trying to do computation. We weren't acting in the world at all. So, like someone tells you this is your dynamics model reward model, and your goal is to return a B star in a policy. In this case, what we're doing is we're acting in the world. And we're assuming we might want to act in the world forever. So this is like, yes. Our agent is exploring the universe forever, and it's trying to maximize its reward, and so this is just going to continue forever. We don't stop. Great. Okay. So these are a sufficient set of conditions. And what I'll do briefly is I'll talk about proving one of these things, which is optimism. So we'd have to prove all 3 of these things for MBIEB. I think that, let me just say a little bit about how this type of construction works. This is a theorem statement. I have not proved to you that it's true. I've just said that this is a theorem statement. This is from, I think it's Strel, Lee, Littman. It's either ICML or UAI 2006. And this is a theorem statement. So this is a theorem where they say this is a recipe for proving an algorithm is PAC. And then they had to prove that under these conditions it's PAC. And the paper goes through that. What I'm going to show briefly, or at least work towards that for the remaining few minutes, is that MBIEB satisfies optimism. Just give you an illustration of some of the steps that are involved with these. Yeah.
So when you're updating your Q tilde,
Yes.
So you are the next action that we take. We are actually acting really with respect to our current estimate of Q tilde.
Up here. Yes.
The last one, where you're saying.
Well, this is the only place we're acting in the world.
So if you're running our update at the end, we are also doing kind of like a policy proof because we are actually saying max over the next A prime of the Q tilde. So why not actually looking at like the average over the actions, the average of the expected Q tilde of SNA over the A's. So I'm just trying to think, so one way is maximizing over the action space of our current Q tilde. Another way is probably sampling your actions. And another way would be taking the expected value of your current Q. So what are the advantages?
Well, this is what this is. Great question. What this is trying to do is this is doing Bellman backups. And in the Bellman backup, we know we want to always do the maximum expected discounted sum of future rewards. So if we're doing a normal Bellman backup, like a value iteration, we would always have a max here. Because you're not just trying to follow any next action, you're always trying to follow the best next action, like in value iteration. If you know the dynamics model and reward model, value iteration, we did something that looked very much like this. This part looked like V of S prime, but V of S prime is exactly equal to max over actions of Q of S prime A. So this should look really like the same as what we're doing with value iteration, but we substituted in the empirical.
So since our estimates may not be actually accurate initially, so I could see maximum not be a good operator to
But we want to be optimistic. So we're using optimism. So we know that if this was accurate, we'd want to take a max. And we are going to not only try to take a max here, we're going to try to add an additional optimism on top of that. So this is still with respect to our empirical Q. And so we're trying to do the same as what we do for Bellman. And you're saying, well, maybe those are inaccurate, and they might be. But in that case, we're still just going to be optimistic, or maximize with respect to our current empirical estimate. And then we're going to add further bonuses in. So we're really trying to, what this is going to end up doing is this is going to end up giving high values to things that empirically look effective so far, or that we haven't tried much. And that's going to give us our optimism. So let me briefly prove that doing this is optimistic. Okay, so okay. So what we're going to try to do is, MBIEB is essentially using value iteration, and we're going to be doing this Bellman backup with this empirical value function. And what we're going to do is we're going to say, let me make sure I write it out in the way that I want to. Okay, so what we're going to do in this case is we're going to assume, this is lemma 7 in the paper, in the MBIEB paper. And it says that under this condition for how we execute, for this definition of MBIEB, then with probability greater than or equal to 1 minus delta over 2, Q tilde of SA is always greater than or equal to Q star of SA. Let me quickly go back. Okay, so what we're going to think about in this case is that let's think about the time steps on which we're experiencing a state action pair. And we're going to think about the random variables that happen in that case. So for a particular state action pair, let's think about the first up to m time steps where we visit that state action pair. And we're going to define xi, having no relationship to the xi as we talked about before, as being the reward we received on that time when we were in that state and took that action, plus gamma times v star of S prime. So this says, so we had a whole bunch of S, A, R, S prime tuples. We can index these from I equals 1 to some number less than m, because we only use m samples. And this is on the time that we were in that state and took that action, what was the immediate reward we got, plus gamma times what would be v star of Si prime. We don't know what v star is. This is just saying, it's just defining something. It's defined in a quantity xi. Okay. So then, in this case, notice that the expected value of xi is going to be equal to q star of SA. Note that this is just a sample from the next state. And then if we assume that all of these are IID, then we can do Halting and think about how many samples do we need until this is going to converge to the expectation. So we're going to say, what is the difference between the expected value minus 1 over k, sum over I equals 1 to k of xi, being greater than or equal to some value beta divided by square root k is less than or equal to e to the minus 2 beta squared 1 minus gamma squared. Okay. This is with Halting. Should really be a little bit more careful about this and do martingales, so it's a little bit loose. But just being, this is following also what they did in the paper, but I think it's more precise to do martingales, but let's do this. So if we substitute in the definition of beta that we have in the algorithm, then this is equal to delta divided by 2, size of our state space, size of our action space in M. Okay. Now notice that if we think about what this quantity actually is, this is going to be equal to our empirical, using our empirical estimates. So something goes I equals 1 to k xi is going to be equal to r hat of SA plus gamma sum over S prime probability, our empirical probability of V star of S prime. Because if you summed up over all of the samples that we had, that would be equivalent to if we had used our empirical reward model and our empirical transition model with V star, which we didn't. We used it with our Q estimate, but imagine that we used it with V star instead. Okay? And so what this means is that, looking at this right-hand side, that R of SA plus gamma sum over S prime, our empirical transition model, of V star of S prime minus Q star of SA is greater than or equal to minus beta divided by square root k. So that's what Halting told us here, because this expected value is Q star. So it says the difference between using our empirical reward model and our empirical transition model with the true V star, which we don't know, minus Q star is going to be at least as good as minus beta divided by square root k. Okay. This is going to hold for all S, A, and time step T with high probability. Okay, so now let's think about what we actually do in MBIE. It looks almost like this, but instead of having Q star, we're going to have our approximate Q tilde. So what do we actually have? We actually have Q tilde of SA is equal to R hat SA plus gamma sum for S prime probability, our empirical probability, times max over A prime, Q tilde of S prime, A prime, plus beta divided by square root N SA. And so now we're going to do a proof by induction. I'll sketch it out quickly. Okay, so we know the base case works because, as I said before, we initialize things optimistically. So we have, by the base case, everything is optimistic. And now we're going to do the induction step where we assume that everything, yep.
Understand the lemma state. Should there be an epsilon in the inequality?
Should there be an epsilon in the inequality?
You start the best in the lemma state on the top. You have the Q tilde is.
But you can have an so this is not the true value. This is just the value we're computing. Now this is the true best. This is just saying that however we're estimating the Q is higher than Q star. Yeah. Yeah.
In the statement of the theorem though, didn't you need it to be greater than Q star minus epsilon?
Right, so if it's greater than Q star, that also suffices. Epsilon could be 0.
And what is the relation of delta? I mean, just take delta.
Delta is an input. Yeah, in the algorithm you take in delta. It's saying how close, with what probability do you want this whole thing to hold? Yeah.
So in this second to last line, you have a capital R, and then
Yeah, these should be the same. Thank you for catching. Yeah, the R's are all the same in this case. You can write these smaller. Thank you for asking.
Are you summing the small r's to get the complete r?
No, these are all the same. Thanks for this. This is the same R. This is the same R as what we have on the right-hand side. This is our empirical estimate, our empirical average of the immediate reward we get in the state action pair. Okay.
How does it relate to Ri? It's a sum over Ri, right?
Sum over Ri divided by the number of samples. So the same definition as the other side. Yeah, thanks for the clarifications. So we have this. We know from the base case that this is a proof by induction. Okay, induction, so our base case holds. And then we want to assume that this holds for Qi, and we want to prove it for Qi plus 1. So we have the base case, and we want to assume holds for I for Qi. All right. So I'll just start to show how we would do this here. We would write out how we're updating our Q tilde of I plus 1 of SA, and that's going to be equal to our R estimate of SA plus gamma sum over probability of S prime given SA max over A. I'm just rewriting this equation. Q tilde, now I'm indexing it by I just so we can be clear which round we're in. So what we have here is that we know that this is going to be an upper bound to V star from our induction. So this is, let's do. So we can just substitute that in. And then this is going to be greater than or equal to, if we substitute in from this equation, we know that this first part is greater than or equal to Q star minus beta. So if we substitute that in, so we're going to replace this part by Q star minus beta over square root NSA plus beta square root NSA, which is equal to Q star. So that gives us our optimism. So this has satisfied the first part of this. I'll just very briefly say sort of what are the other directions that have happened since here. So one of the key insights has been about what these bonus terms should be. This bonus term uses almost no information. What is the information it's relying on? It's relying on the range of the value function. So 1 over 1 minus gamma is the maximum value you could ever have. So we have a bonus term that depends on the maximum value you could ever have and the square root of n. And this really comes out of sort of how quickly our estimates can be concentrating, which we can see from concentration inequalities like Halting. So one of the insights that's happened over the last 5 to 10 years is that we should use better concentration inequalities and use things like Bernstein bounds, where we look at the variance of the value function. And so that ends up allowing us to save some of these dependencies in terms of the size of the state space. So I didn't write it out here, but in these sort of initial bounds, it would depend on sort of something like 1 minus gamma to the 6th, and often it would be S squared A dependencies. And by using tighter constant integration qualities, that's what's allowed us to have much tighter bounds, both in terms of problem-dependent results and problem-independent results. And one of the questions that we have today for the recitation will be as a chance to think about sort of some of the regret bounds that we have as well. And that'll be it for today. And what we'll do tomorrow is we'll talk about another aspect that I think is really important for trying to create algorithms that are much more sample efficient, and thinking about this for when you're given a batch of existing data and how you should use it to induce an optimal policy. Thanks.